everybody. Welcome to our webinar, Automation using Python, an introduction to the isystem.connect API. Alesh, can you unmute yourself, please?
Yes, hello, welcome to everyone to our webinar, yes.
Okay, thanks. My name is Errol Simsek. I'm the moderator in this webinar, and as you have heard, Alesh Kojia is our speaker. He will lead you through the webinar today. Alesh is one of our scripting experts, field application engineer, and with an experience of about 20 years in the embedded space. So he will talk about this topic today. Next slide, Alesh. Just to give you to do some housekeeping here. You are all muted, so it's not possible to have a discussion. Too many people in the line. The chat functionality is activated, so you can talk to me. If you have questions, I can react. Questions in general can be placed using the question writer in the webinar menu in a written way, and I will pick some of these questions at the end of the webinar to ask Alesh to answer them. All other questions will be then answered by email afterwards. So today's webinar, after the webinar, at the end of the day, if you are an experienced user or just a isystem BlueBox beginner, at the end of the day, both of these groups will have a huge overview of this API and the possibilities you have with this API. We also entered a couple of links for free trainings and examples, and we are confident that you can start scripting right away using the interface. We have a download possibility for the handout of this webinar that you can find using the handout writer. It's a PDF version with all links inside. So now enjoy the webinar. Go, Alesh.
Okay, hello once again. Welcome. Today's agenda will be, first, I will make short introduction to our tools, isystem tools. Then I will make a short introduction to scripting, what is our approach. And later I'll go step by step over some major controllers, managers, functionality of the API. At the end, I will also make short introduction to isystem.test API and also isystem.fnet API. So let's start. iSystem debuggers, the latest addition is IC 5700. It has so-called FNet ports. Beside the debug and trace ports, we can extend these FNet ports and we can connect the external add-on modules. One of it is CAN-LIN module. We can trace CAN-LIN signals buses, and we can also generate CAN-LIN messages to the buses. The next module is so-called ADIO. It has several digital IOs and also analog inputs, outputs. Both of those CAN-LIN modules can be connected over this FNet port to our debugger. The IC5000 can have so-called FNet hub. This is so-called addition. We offer additional FNet ports, so we can connect more external devices. On top of that, we have also at the bank a special Ethernet port that is used for synchronization, timing and debug synchronization. So we can put two debuggers, two IC5700s together, and we can debug and trace in synchronized mode. It means we can step one and also the other debugger that controls other CPU, it's stopped or can run, etc. And additional step, we also provide so-called active probes. These are so more advanced debug connection, debug trace connection. We offer more bigger trace throughputs, higher speeds, longer cables, and with these active probes, we can also enable, as mentioned, the synchronous debugging over to IC5000 debuggers. So the next piece is winIDEA. winIDEA, it's a debugging IDE. It has typical functionality as an IDE like watches, memory windows, disassembly windows, and so on. And all the configuration about the hardware devices, it's stored inside winIDEA as a project. So whatever is configured here, all the hardware device, it is stored here inside the winIDEA configuration. Also, another very important feature is so-called trace analyzer. Trace analyzer is about tracing. So we have trace, we can trace program data, we can offer real-time operating awareness, and then from these traces, because we have timestamps, we can measure up to, it depends on the CPU family, up to a couple nanoseconds of resolution. We can measure timings of the program, code execution, task switches, and so on. And we can also measure the coverage. When we perform tests, when we execute code, we can measure coverage without any instrumentation. And of course, we also offer special tools for further timing analysis that we can calculate, measure, let's say, propagation delays, because we can, with this trace analyzer, we can also measure messages on the buses that were, measured together with this CAN-LIN add-on models and so on. This is about our toolings. Next tool that is also part of our system is so-called testIDEA application. It's an application where you can configure unit or system test. You don't need any instrumentation of the code. You don't need to recompile the debugger, and our technology will perform, for instance, unit tests, each one in consequence without any problem for you, without any additional work or compiling for you. You can have additionally automatic stubbing if you want to stop, fault injection, you have a reporting system, and this testIDEA also reuse the completely trace analyzer and the system which is configured with the winIDEA. Okay, the next slide. This is a picture how we prepare and how we handle our automation hardware and software. We always run the scripts. We always have the target and our debugger. The nickname for our debuggers, for instance, for IC5700 is BlueBox. And this is always connected to target over different debug and trace ports. On top of this, the complete project is stored inside the winIDEA, our IDE debugger. All the configuration, all the settings are stored there. And then on top of that, we have several APIs. isystem.connect API, this is how to automate our debugger. isystem.test API, this is how to perform testing like stubbing, reporting, and isystem.fnet, it's how to automate external fnet devices like CAN, LIN, and also we have kind of operation system inside the winIDEA like trigger system and so on. All those things can be automated. And then we have the testIDEA application running with the test specification, or we can go directly with the scripting. We can start Python scripting or other languages. And also inside the testIDEA, we can generate complete self-alone running Python script out of this testing. Yeah. So we can also prepare with this system continuous integration, testing, and so on. And while talking about continuous integration, my next webinar will be about the continuous integration using Jenkins. So I will explain how to configure and how to run this system for continuous integration. isystem.connect API, we can offer you several SDKs for Python, Java, C#, C++, MATLAB, and LabVIEW languages. What do you have when you install the SDK? You get the libraries, you have documentation, a lot of examples will be there. So you can start fast with some examples and start coding immediately, and you'll get also the installer. For instance, for Python, what you need to install your Python installation, like Python 3.6, and then you install our isystem connect API, and you copy the isystem connect DLLs as a side package to the Python installation. Here I have a samplet of code for instance, for the C#, like, the C#, of course, when we are looking into our examples, there is slight difference between the Python, of course, due to language. For instance, here we need to define the type of the class, and then with the new we create an instance of the class. This is just a short example of the C# isystem connect script. So the hardware configuration for our scripting scenario could be like that we run the scripts and winIDEA on one host PC, but also our API support. Okay, sorry, I'll go back. Support, okay, just next one. Supports this configuration. It's a local host that is connected to our target, and here is installed the winIDEA and project for debugging winIDEA project, but we run the scripts on the remote host over the Ethernet, and this is also supported with our APIs. Okay, then the next, we can also run Python script directly through the winIDEA. If you code small scripts, you don't need complete Python installation. You can still start running with short script, and for debugging, you can run it completely out of winIDEA. So let's jump into the first simple script. For Python, we import isystem connect as an IC, and then we need to create an instance of the connection class. We need to open winIDEA session, and we create so-called debug facade. Debug facade is a class that have a lot of functionality that are needed for debugging, like breakpoints, run control, etc. And in this case, we will flash the binary, all the information, how to connect to the target. It's already inside winIDEA. What is defined there for flashing, it will be flashed down, and with this next instruction will run until main function. So this is really short script that you can get a sense that it's not really hard to start. And this example is actually you can generate out of winIDEA. We have a template that it's really simple to start. So basically, I have already explained the connection manager. We connect to last open winIDEA. Then with the debug facade, we flash the binary, and then we run until main. Okay. Okay, next slide. Connection manager. This connection manager manage our connection to winIDEA. First, we can start we can start over the Ethernet as mentioned, but we always need to connect a certain winIDEA project that is installed inside the let's say target PC, and here we can connect over USB or Ethernet to our debugger, and all the settings are described there, how the connection to the actual target is there inside the winIDEA. So basically with the connection manager, we start remote or local connection. We open the last open winIDEA session. We can discover the winIDEA project that is correct, the right one for our scripting. We can check the connection status, and of course we can disconnect. Okay, this is one example of the short example of Python code. Here we configure exactly the right one project and we open it over the Ethernet. So this is from our example code. You can always go to our web page and look to our examples there, and then you can start and you can modify and then you can start coding. It's easy. The next control that is very important is so-called debug facade. The debug facade contains functionality of the loader controller. This is flashing, execution controller, data controller, breakpoint controller, and address controller. Okay, the loader controller, this was functionality I explained before. We can load flash with the loader controller or debug controller. In this case, just for demonstration, I created an instance of loader controller, and then the flashing is controlled over the loader controller. Loader controller has maybe a little bit more extra functionality that's included inside the debug facade. How to download the binary? For instance, we can download as I demonstrated with the previous slide, but we have possibility with so-called target download. So we take whatever ELF it's available, and we can overwrite and flash exactly the right needed ELF. This ELF could be completely different, the one that is defined inside of winIDEA. And we have also typically possibility to verify the download. This is a short code for that. Then how to change the download file list. This is a winIDEA settings here. For instance, we have multi-core project with several ELF files, and we need to reconfigure, in this case, the winIDEA settings, meaning after scripting, the different list of download files will be stored inside winIDEA. We can do this with so-called IDE controller. IDE controller actually controls the settings of winIDEA configurations. And inside winIDEA, we have a lot of drop-down menus, checkbox. Even if these menus and checkboxes are not supported directly with the APIs, we can still offer you support. You can ask us, and you can, as a support, we can write you on short examples with set options inside winIDEA controller, how to change 99% of what is possible inside winIDEA. For this, for instance, here we can access this list, and we can change the list of download files, even if we don't have directly API that takes care about this. Just write, always we have great support. You can always write, ask the question how to do this with the scripting, and we will help you. Typically, additional features of the IDE controllers are like resizing the window size, change the winIDEA configuration, say save and close documents, close views, etc. One typical example use case is also we want to read the winIDEA version, because we always want to know whether we open the latest one, the right winIDEA version, because a lot of winIDEA versions can be installed in parallel on the PC. The next use case is how to connect when we have the multi-core connection project, meaning we have CPU with many CPU cores, we can use so-called multi-core configuration connection manager, and we need to define what are the names and types IDs of so-called primary core and the secondary cores. For instance, in this case, this is PowerPC. We need to define what are those IDEs. Then we need to connect to the primary, to the main core. And when we establish the connection to the primary core, we can create debug facade that controls debugging on the main core. And after the connection to the primary core, we can also open and connect to every additional secondary cores of that CPU, and we can create additional instances, for instance, of debug facade. So we can debug, we have complete control what is running on the first main CPU core and what is running on those secondary CPU cores. Okay, and we made the connection with the use of multi-core connection manager. The next very important class that is also included inside debug facade is so-called data controller. With the data controller, we can access the debugs, the variables that are part of the debug symbols, meaning variables, CPU registers, SFR registers, meaning special function registers of the CPU, raw memory, and we can also access expressions. For instance, in this case, we will read and check a variable. This is debug symbol. This variable is global variable. It has defined debug symbol, and we will read it in real time, meaning without stopping. In this case, we will modify in real time the same global variable. And we can access in real time CPU registers. I mean, if you want to raise the exception handler we want to test, we can crash, we can modify the value of special function. I mean, the stack pointer, for instance, we can corrupt program counter. We have unlimited opportunities to do with our scripting, and handling the expression is meaning like the C expression. We don't need to, in this case, for instance, to read, let's say, several variable. We can just prepare what is the value of an expression, like if the variable number 1 is equal to number 2, we just evaluate this expression. The return value will be true or false. Yeah, we don't need to read first variable and then the second variable with the Python and then check whether the variables are equal. So we can use expressions. The next class and the next feature is so-called batch access. When we want to, let's say, to have data acquisition with a lot of variables, we can use so-called batch access. With the batch access, we'll have the most exact timing of sampling. Why? Because the Python that is running on the host PC, it's not real-time. Windows is not real-time operating system. And with the batch access, the script sends the list of the variables that will be either written or read out to debugger, and this debugger then performs in a loop the sampling. And then the timings are the most exact. For instance, this is a short example of the batch access. We need to prepare in advance the list of variables. Then we need to define what are the number of items in this list, what are the numbers of loops, the runs, and then what is the timing interval, and then the batch access will return the sampled variables, for instance, in this case. This is, of course, real-time access. The next very important controller is so-called address controller. The address controller provides us information about the debug symbols, about what are the raw addresses of, for instance, functions. We can get the address of the function, the raw address of the variables, or we can have the address of the element of the structures. So we can also get the number of the source line. This is important if you want to put the specific breakpoint on the specific line, or and so on. An example, for instance, the use case for the address controller could be how to initialize the structure. When we are testing, for instance, the complex structure, even if we have the new binary with a different number of elements of the structure, we can read out with the address controller what is the size of the new version of the structure, and we can get the information of the size, of the types, of the elements, and we can still modify with the script on the fly, even if the binary is actually changed. This is, for instance, one use case. The next use case will be the measuring of the stack usage. We need to figure out the addresses of the stack. Okay, sorry. What is the start, what is the end of the stack address. Then we can use a script to set the stack before startup with a special, let's say, pattern, and then we can run the execution of the program. We can stop or read out the stack pointer. This is the current stack usage, and we can analyze the stack memory and see what was the maximum or minimum usage of those stack, because we see up to certain level where the stack memory was overwritten over the pattern memory. So this is one short example. We can modify scripts. If you have a real-time operating system, we can figure out what is the task stack. Of course, a lot of stacks have they have so-called stack measurement, meaning the stack, the real-time operating system structure has this information. Then we just need to read out from those variables raw memory. We can read from the structure what is actually the stack usage. We can have a different approach to control, to monitor the stack usage. The next use case would be so-called stack frames. winIDEA has so-called call stack window view. We can see the call hierarchy of the executed program. So we can analyze with the stack frame for each call stack context, what are the local variables, what is the stack usage, etc. This can be done with this example, which analyze the stack frames, and it prints out the local variables that are stored inside the stack. So if you want to see the core hierarchy and the previous local variables of that call stack context, we can use this example of the Python script. The next very important execution controller is so-called execution controller. With the execution controller, of course, we control the execution, the run, stepping of the program. We have so-called run methods of this controller, like run until address, etc. These are so-called non-blocking Python execution. We need to check with the Python script whether the execution is still running or whether the CPU is in stop. Meaning we can use wait until stopped or wait until running function to check what is the CPU status. The next let's say class of this execution controller is the functionality of stepping. The stepping is blocking, means it will always execute it, that the Python can continue. We have so-called stepping high, meaning we step on the source level and step instruction on the low. It means on the binary disassembler level. So we can step on the source or we can step on the binary level. We have also possibility to use go to. It means we can stop the execution. We can completely jump to some other part of the code, but of course, we should know what we are doing because we can easily crash the execution, but still it's possible to use this with the Python. We can also call a function directly. For instance, if you have void function that configure a certain driver, we can call it, or we can manipulate and prepare and push on the stack all the variables and then call the function completely out of context. This is possible with our execution controller. The next very important controller is so-called breakpoint controller. We can enable, disable, configure, clear breakpoints. We can use so-called, also we can enable and use software breakpoints. This is a functionality when, for instance, for low-end CPU, where it's just we have maybe 2 or 4 or not enough breakpoints available, we can enable software breakpoints, meaning the debugger will insert into the execution so-called stop instruction. This is so-called software breakpoints. We can configure all those functionality with the breakpoint controller. For instance, this is the simplest example. Here we'll set the breakpoint on the beginning of this find function. We'll run, we'll check if the breakpoint is hit, and when the breakpoint is hit, we will read out with so-called monitor access the value of the variable. This is a short example of usage. Of course, we can configure inside breakpoint controller the conditions, the hit numbers, etc. I have a short example of fault injection that will use the functionality of those controllers that I have just explained. We have a short, really short C code function called temperature read function. This will call the hardware, the sensor read, and when this sensor hardware function will read out the temperature, we will insert a breakpoint here, and then we'll modify the local temperature variable in that way that this alarm will be raised. So we will step 2 times. Actually, the Python script, the short part of the Python script will be like this. We will analyze where this if statement, source code, like if, is located. This function will search inside the function, search for the text and the match, and when this line location is with address controller is known, we will put and use this line number and set the breakpoint inside this module, and then we'll execute and run until it's stopped. Then we'll modify this variable, and then we'll perform 2 steps in order to get to here. We will modify that is bigger than 99, so we will raise an alarm. This is short example how to prepare fault injection. The next classes are about trace analyzer. So we have so-called analyzer controller, and part of this analyzer controller are trace controller, coverage controller class 2, coverage data controller, profiler controller, and profiler data controllers. Okay, I will explain more in detail coverage controller. The coverage controller implements the functionality of the trace for the coverage measurement. We will configure the coverage measurement. For instance, what is the what is the range of coverage measurement, what is our interest. Then we can run coverage measurement. At the end, we store the measurement. And with the coverage data controller, we will analyze the coverage measurement. We will parse the stored XML file and we can print out the details. This is a short example of this controller. We need to define so-called trace file. This trace file contains all the configuration, trace configuration, and also the measurement of the tracing and coverage measurement. We don't need to create a trace controller. Whenever we create just coverage controller, it means somewhere the script will generate automatically derived trace controller. Then we need to define the scope. In this case, the scope of the coverage measurement is everything. Then we start coverage measurement, we'll run, we'll stop sampling, and then later we can store the coverage results as a XML, for instance. Very similar is for the use case of profiler controller. Profiler controller is about timing measurement. So we first, with the profiler controller, we'll configure profiler functionality of the trace analyzer, then we'll run profiler recording and we'll export the measured result into XML file. And with the profiler data controller, we can pass and get the information of the measured profiling. We can profile function execution and data execution, real-time tasks, etc. Okay, this is a short example of the profiling script. Here we once again create a trace file. We'll create completely new trigger that will start at this function. It means we will start measuring timing of the execution when this function is hit. Then we'll measure these two functions, what is the timing of the execution, and we can also measure a variable. This is configuration of the measurement. Then we'll run and stop the execution and the profiling. At the end, we'll store the data into the XML file. This is this part of code. Very short, I will explain also the hill controller. This is about the ADO signals, and also if you have older debugger version, you can have so-called hill controller on top, ADO controller on top, and you can generate output or read the digital IOs. But currently with the latest FNet API, we have much more powerful and API that control these signals. This is, let's say, I would suggest this hill controller for the older type of debuggers. So next short introduction would be about isystem.test API. This is API about that execute testing. So we can always combine isystem.connect and also isystem.test. With the isystem.test, we just have several other possibilities. We have reporting, we can have testing, we can provide results, we can generate and create unit tests, system tests, we can have stubbing, we can use tracing, coverage measurement, and so on. We have mainly two bigger groups of classes. One is about test specification. Here we define what is the test vector, name of the function, values, expected results. And the second group is about the execution and running the testing. This is a short example of the usage of the isystem.test. Here we see we import the isystem.connect and isystem.test. But what is the really important with this? We start executing, we flash what is typically, a short quiz I demonstrated before many times, this functionality. And here it's about testing. Here we create a test, an instance of the test case. And we just triple quote, we put inside triple quotes the test specification. This is YAML test specification. It will run the unit test on the function called max. These are the input integers, and this is our expected result. So basically, we just quote the test specification and we execute, and this will say whether the expected result has passed, whether the test has passed if the expected result is match. Of course, this is very short function which will find what is the biggest of input integers. So this is, but you'll get the impression it's not really hard to start with the testing too, and you can get at the end also the reporting. The next API, which was just released, it's so-called FNet API. This API, it's about controlling FNet devices. So we can connect into IC5000 debugger several external modules like CAN, ADIO, and this API is how to control this functionality. We always need to connect to winIDEA session when having FNet, because the winIDEA contains all the functionality about the FNet configuration, and then we can control ADIO, CAN module. We have internally inside the winIDEA functionality of counters and triggers and events. We can output, generate, combine several features of this system of combined devices that are part of the FNet network. For instance, a part of the main controllers would be controlling digital ports of the IDO, controlling input of analog input of the IDO controller, controlling output, analog output of the ADIO, configuring and controlling and measuring SPI, then measuring power sense control of the ADI. Then we have how to we can control CAN of the CAN add-on modules, and we can also control and configure counters and triggers. Each of these controllers has so-called configuration subclasses, meaning the static configuration of the CAN boxes. Operation subclass means looking from the complete structure inside the winIDEA. We can have connected several add-on modules. We can combine this for trigger system, etc. And so-called runtime control, meaning in runtime while we are running, executing, we can change, we can inject CAN messages, etc. We can change the digital outputs, analog outputs, and so on. This is a short example. There's a lot of functionality there, but here we have import FNet, and we then control and configure the ADIO levels, the names. Then we can run the complete system. We can have the trigger system, like these lines here. This trigger system can, when detects several inputs, can generate outputs, etc. Okay. So I'm very close to the finish of my presentation. So this slide, it's kind of overview of the isystem.connect main classes. Here we can have execution controller, connection manager, which first we need to connect. Then we can have execution controller, address controller. This is about the debug symbols. Then we can have breakpoint control about setting, clearing breakpoints. Then we have data controller, how to access memory variables, modify them. Loader controller, how to download flash binaries. Then we can have IDE controller, how to configure winIDEA settings. And then we have coverage measurement and profiling. These are just, I listed here just a few of the main controllers. Most of them are parts of so-called debug facade, but in reality, inside the isystem.connect, we have many more controllers. More really, you can go to our web page, and you'll have complete documentation about our classes, controllers. You'll have a lot of examples there. So my presentation mainly is just introduction into isystem. There is a lot of more features. You can always ask our support and send questions to us, and we'll help you. But you can always look to our documentation that is available on the web page. And of course, part of our system is also we have also trainings how to use testIDEA application. There is a training sample example project, step-by-step training how to efficiently use testIDEA, and also how to efficiently use winIDEA. All those trainings are available on our webpage.